Okay, we are picking up with lesson 2.4, which is called the chain rule. And it's kind of our last derivative rule we need to learn. We've done power rule, product rule, quotient rule, all the trig rules, I guess is what you could say. And now the chain rule allows us to take derivatives of composite functions. Okay? So composite functions is kind of when you have like one function kind of like inside another function. Or you might have heard of fog or goff, I guess is what you used to call it. Where you have like f of g of x or g of f of x. So how do we take the derivative of something like this? So we're just going to go through and kind of practice identifying what our outside function and inside functions are, and then rewriting these functions as composite functions, and then that'll kind of help us when you talk about how we take the derivatives of these. Okay, so I think it's almost easier to identify like your inside function. So I look inside these parentheses here, and I see that 3x minus 5, and that's being raised to the 7th power. So I cannot think of my inside function as that 3x minus 7 piece, and my outside function is, hey, I am raising that to the power of 7. Which would make sense if I took f of g of x. If I were to plug 3x minus 5 into f of x, which is x to the 7th, we would get that 3x minus 5 to the 7th. Okay. Sometimes I count when I teach composite functions, like in algebra or pre-calc, I like to use a little like box thing like this. You kind of just block part of it out here. So again, inside function is easy to detect because it's usually something like underneath the radical or in parentheses. So my inside function here would be that polynomial piece, the 11x squared minus 2x plus 1. And if I kind of block that off to see what my outside function is, it looks like it's a sine of some value, x. So let's kind of test this out, see if it works. If I take f of g of x I identified as 11x squared minus 2x plus 1. If I were to plug that in to f, it would be the sine of 11x squared minus 2x plus 1. And that would work. Last one. Inside my radical, I see the secant of x. Okay, so if I block out that inside piece, I see all I really have left is just the square root of x, so that could be classified as my outside function. And just to double check if that works, f of g of x, which is the secant of x, plug that into what we call f, which is the square root of x, and we get that original function, square root of secant of x. Okay. So just like with composite functions, you want to be able to identify kind of like what's inside and outside when we find derivatives. We're going to have to do the same thing. So here's the chain rule. If you are taking the derivative of a composite function, you have to take the derivative of the outside function, leaving the inside function kind of the same. And then here's like the extra link. This is why it's called the chain rule. You got to remember to multiply on the derivative of like the inside function. Okay. So I kind of like this. This is like an informal definition, the outside inside rule. You got to take the derivative of the outside function with respect to the inside function, leave the inside function the same. And then here's that extra chain part, multiply by the derivative of the inside function. But it says times, it means multiply. Okay. This is a textbook definition of the chain rule. And you can kind of see it right here. If I have a composite function, f of g of x, take f prime of g of x, leave the inside alone. And then times it by, here's the extra link of the chain, times by the derivative of the inside. And that's the part that people always forget. They'll like take the derivative of either like both pieces at the same time, or they'll take the derivative of like the outside function and forget that extra like of times by the derivative of the inside. Okay. So let's do those ones from our example. This rectangle's a little big for this problem, but sometimes I like to just block my inside function. So we just talked about this. Obviously, the 3x minus 5, I'm going to kind of just call that my inside function. And if I were to take the derivative of this red box to the power of 7, I would use power rule. And I'd bring down the 7 and say it's 7 to the red box, drop 1 from the power. Now what you do is you keep everything in the red box the same. So we just keep that as 3x minus 5. So there we essentially just took the derivative of the outside. Okay, my outside function was x to the 7. Bring the 7 down, drop 1 from the power. Here's the chain rule part. Times multiply by the derivative of the inside function. So times the derivative of 3x minus 5, which is just 3. There's the length of the chain rule. The only thing I would do to simplify this is multiply the 7 and the 3 together. And you get 21, 3x minus 5 to the power of 6. Okay, so we haven't done any problems like this where we've had to multiply by like that extra chain. We've only done like single terms or product and quotient rule. Okay, next one. I have the sine of 11x squared minus 2x plus 1. So my inside function is that polynomial piece. I'm just going to kind of block that off for a second. So the first thing I do is find the derivative of the outside. Derivative of sine is cosine. Cosine of red box. Okay, red box is just 11x squared. Don't take the derivative of the inside in the first step. You just do the derivative of the outside. Leave the inside the same. Chain rule times the derivative of the inside. Ooh, polynomial, nice. 22. X, drop 1 from the power, minus 2. The only thing I'd maybe do is write that polynomial piece like in front of my cosine. You'll probably see it more commonly written this way. Definitely don't need to do any distributing or anything. Leave it kind of in that factored form. Okay, make sense? It's a chain rule. We're just going to do a bunch of examples today. All right, my inside is secant of x. I'm just going to kind of cover that up. Well, let's rewrite this as a power first. Anytime I'm a radical, I'd rewrite this as a power. So secant of x to the 1/2. Okay. So now, cover up my inside. Now I'm going to take the derivative, which would be, I bring the 1/2 in front, red box, drop 1 from the power. Okay, whatever is my inside stays the same. Chain rule part, now I got to times the derivative of the inside. Which derivative secant is secant tangent. All right, a couple things we could do here. When we multiply these together, because this is really like secant to the first power, we could just add the powers together. So negative 1/2 plus 1/2 would give me the secant of x to the 1/2. So then I'd probably just rewrite this then as a radical as the square root of secant of x. Like that. Probably bring the tangent in front. Usually we write radical terms last. And then we just have that 1/2 that's left out in front. Everything's being multiplied together. So you're kind of doing the chain rule, you guys, anytime you do power rule. So say we have x cubed. I'm essentially doing the chain rule here where I do this times the derivative of my inside function is just 1, right? So you're really kind of doing the chain rule every time you do a derivative, but now we're looking at functions where it's just not x. I like this one. Okay, I'm covering up my inside, and I see I have red box squared. I'm like, no problem. I would just bring the 2 in front, red box, drop 1 from the power, that just be to the power of 1. You don't need to write the 1. What is red box? Red box is 1 plus cosine of 2x. Times the derivative of the inside. Okay, careful here. Derivative of 1 is just 0. Derivative of cosine is negative sine. I can have a double chain rule here. I kind of have a little composite function again right here. So it'd be negative sine of, keep the inside the same, 2x. But then what else do I need to multiply by? 2, the derivative of the inside, times by 2. A lot of people would forget that. Times by 2. Ooh, quite a few links on that chain rule. Okay. So the only thing I would do to simplify this, we got 2 times 2 and times negative 1. I'd write that as negative 4 sine of 2x, and then just leave that as 1 plus cosine of 2x. Obviously, you can have those in any order. Again, usually on like a multiple choice type of situation, you'd probably see leaving the 2-term factor is usually kind of like listed last. Okay. They're going to progressively get harder. But they're fun. Any questions so far? Do you like the box? Ooh! X cubed times 2x minus 5 to the power of 4. Now, we could, if we wanted to, distribute out 2x minus 5 times itself 4 times and then distribute through an x cubed, but that sounds like a lot of work. Okay? We could recognize that we have a product here and just use product rule. That's definitely how I would tackle this. Where I see this is my first factor is x cubed. My second factor is 2x minus 5 to the 4. Product rule. Is first factor times the derivative of the second factor. Now when I take the derivative of the second factor, I'm going to need to use chain rule. Okay, so think of it as you have red box to the power of 4. So it would be 4 red box cubed times the derivative of the red box. All right, what's in that red box? It's 2x minus 5. Chain rule times the derivative of the inside, which is just 2. Oops. Okay, I'm not done. That was just first times derivative of the second term. Plus second term, 2x minus 5 to the power of 4 times the derivative of the first term, 3x squared. Okay, let's clean it up. Here I have 2 times 4 times x cubed. So I could write that as 8x cubed times 2x minus 5 to the power of 3. Don't ever worry about having to actually multiply that out. The answer would be left like in this factored form. And over here, the only thing I would do is I'd write that 3x squared term in front of the parentheses. Yeah, the only other thing you might see, like on a multiple choice, that's it though, we're going to leave it at factored form, is maybe they would factor out 2x minus 5 to the third. And they don't usually do this unless it's like a fraction or like one that you can kind of like simplify more. But I could factor out 2x minus 5 cubed, and that would leave me with 8x cubed plus 3x squared. Now if I factor out 3, I still have one of those left over. And then maybe, you could distribute that. So let me just do this quick here. We get 6x cubed minus 15x squared. So then that would give us 14x cubed minus 15x squared. That could be like another answer. For the most part, it'll be left like this. But they could factor out what's common. There are a couple examples where we do that. Okay. Really, folks, if you think about it, our first step was calculus. The rest was just algebra. Okay, here I see my inside function is all that nonsense. So I'm going to have to use chain rule. So derivative of tangent is what? Nope. This one's not negative. Second guess?
Secant x tan x.
That's secant. You're close. It's secant squared. Tangent is secant squared. So secant squared of red box. What is red box? 5 minus sine of 2t. Something I like to do too is I like write a little multiplication symbol right away. So remember, hey, I got to multiply by the derivative of the inside. All right, so the derivative of the inside, 5 is just 0. Negative sine would be negative cosine. Think of that as just a constant in front. Negative cosine of 2t. Second link times by 2. Derivative of that inside. Okay. So here, all of this is inside the secant squared. So the only thing you could do is, kind of multiply the -1 and the -2 together, and I'd probably write this one first. Totally, obviously don't have to, but this is more commonly what you'd see the back of the textbook say. Nothing we can factor out at all. They don't look very simplified, do they? They look more complicated than they started. If you really wanted to check your answer, you could type this in your calculator. You could type this into your calculator. You could do in y3 the derivative of this, and we should get the same graph. Okay. Now, when we raise trig functions to a power, it's normally notated this way with the power like in between the sign and the argument. Just know this means the same thing as this. And if it helps you to rewrite it like this, you can. This means the same thing as you have the sine of 7x being cubed. Okay, this is just for some reason how they decided to notate it with trig functions. So really think of this as your inside is that sine of 7x. So we have the red box being cubed. So that would be 3 red box squared. And then I like to put a little time symbol. So remember, I will have to multiply by the derivative inside. Okay, my red box is sine of 7x times the derivative of the inside, derivative of sine is cosine of 7x times what? 7. Another chain rule times 7. Again, you really did this. All you've learned so far is the derivative of sine is cosine. You really did times by the derivative inside. The derivative should have been 1 every time you've done this. So you haven't had to think about it. Okay. Let's see. All I could really do is multiply the 7 and the 3 together. And then I'd rewrite this then as sine squared of x in the correct notation. Cosine of 7x. Okay. How many more do we have? 5 more. Anytime I see radicals, rewrite as powers. And even in this case, I would rewrite it by bringing it to the numerator and writing it as a negative 1/2. Okay, that's going to make your life way easier. Hopefully we're kind of getting in that habit now. So my inside is 2x plus 1. And my outside is 3 red box to the negative 1/2 power, 10 over c. So trying to find the derivative of that. Multiply the power in front, that's negative 3/2. Red box, drop 1 from the power, negative 1/2 minus 1 is negative 3/2. Okay, keep what's inside the same. Multiply by the derivative inside, which is just 2. All right, now these are when they kind of get tricky when we have fractions and when we have negative exponents, because we know negative exponents aren't simplified. These two cancel each other out, they divide by 2 and times by 2. So then I kind of get to here. This one's not too bad. All I got to do is move that negative exponent to the denominator. 2x plus 1 to the positive 3/2, and I have negative 3. It's being multiplied. Recognize if this is rewritten in radical form, which it could be, that this would be the same thing. But usually, if it's something that's not like a perfect 1/2 power, usually they just leave it in fraction form from what I've noticed. but that would say the same thing in my denominator. Okay. Little application problem here. If my position function is tangent of 3t squared plus 2, find the velocity. What do we know with the relationship between position and velocity? Position and velocity. Go ahead, Dalton.
Velocity can be negative or positive.
Okay, yep. Velocity can be positive or negative. Speed. What else do we know? Between position and velocity, like their relationship. Mark?
Is velocity the derivative of position?
Exactly. Velocity is our instantaneous rate of change of our position. Okay? Our derivative of our position is velocity. So they're really just asking us to find the derivative here. All right. So I have tangent. Okay, guys, here's a chance to redeem yourself. What's the derivative of tangent?
Secant squared.
Secant squared of red box times derivative of red box. What's inside the box? 3t squared plus 2. So times the derivative of the inside would be 6t, and then derivative of 2 is just 0. All right, so I would finish this by putting that 6t in front of my trig function. Okay, I give you a whole lot of room for not a lot of work for that one. The next one takes a little bit more work room, so you might need to use some paper space. Okay, are these too easy? Should we step it up a notch?
Do we have a choice?
No. I know. Just in case you said, yeah, let's do it. Then I go with it. Okay, these ones, I like these problems. So I threw in just like 3 kind of like tougher examples, but it's just some tough algebra, but it's nothing you guys can't handle from what I've seen with your algebra skills. So let's start with A. And I like it because product rule and quotient rule are mixed in here too. So when I find the derivative of this, I recognize I have a product here. I have a first factor, and I have a second factor. And really, before I even start differentiating, I'd probably rewrite that as a power. I'd probably say, okay, I have x squared here times 1 minus x squared to the 1/2 power. The good news about the tough ones is they're really satisfying when you get the right answer. Okay, f of x, usually you'll see f prime of x for the derivative. So we got to do first term, x squared, times derivative of the second term. And this one, it's looking like a composite function. Looks like I have an inside and outside, so I'm going to have to use chain rule, where I have the red box to the 1/2 power. So bring the 1/2 power in front, 1/2, red box, drop 1 for the exponent, negative 1/2. What is red box? Red box is 1 minus x squared. Don't forget the chain rule part, times the derivative of the inside, which, careful here, it's negative 2x. Okay, we're not done. That was just my first part of the product rule. First times the derivative of the second. Plus second term times the derivative of the first term, which is just 2x. No, it's not bad. Okay. I'm going to use my green one to kind of simplify here. So in my first step, where I multiplied first times the derivative of the second, I see I have a 1/2 and I have a 2. Those would cancel each other out. And then the only other thing I'd maybe do is multiply the x squared to the negative x together. So I would get negative x cubed, and then I have this piece, 1 minus x squared to the negative 1/2. Okay. Over here, on my second part, where I did the second factor times the root of the first, there's nothing I can really do here. I'd probably write that 2x in front. All right. Now I have essentially two terms. Negative x cubed times 1 minus x squared to the negative half power. 2x times 1 minus x squared to the 1/2 power. So I see two things that these have in common that I can factor out. First of all, they both have an x. So I can factor out an x. And then I could also factor out 1 minus x squared to the negative 1/2. Because technically I do have that here, and we'll talk about the math of that in a second. Let's take this piece by piece. First of all, if I factor x out of negative x cubed, I'd be left with negative x squared. And then I factor that entire 1 minus x squared to the negative 1/2 out. So that's gone. Here, if I factor an x out, I'm left with plus 2. All right, now the math over here. When you're really factoring, you're doing division. So if you do you divide this out, you're really just subtracting these powers. Okay, that's like the algebra we're doing here. And 1/2 minus negative 1/2 is 1. So I'm left with 1 minus x squared to the power of 1. You don't really need to write the 1 there. But this helps us for two reasons. One, I'll be able to take care now of this negative exponent by moving it to the denominator. And two, it kind of got rid of that fraction exponent from me right there. Yes, sir.
So how'd you get rid of the negative x cubed?
I factored an x out, so I'm left with negative x squared. Yep, I factored an x out, and then I factored this whole thing out. Because technically I have common factors of 1 minus x squared. I factored out a negative. And this, like, I don't want to say it's a trick, but this strategy will come up a lot. Because, like I said, it kind of took care of this fraction exponent. And now we're able, that this is a factor, we could, like, move that whole thing to the denominator eventually to get rid of that. And in here, now we have some simplifying we can do. Since this is raised to the power of 1, we can distribute this 2. Okay, so let's do that. So I get plus 2 minus 2x squared. All right, now I'm going to do the last couple steps kind of in one here. So in here, I could obviously add negative x squared and negative 2x squared and get negative 3x squared plus 2. And then I'm just going to kind of leave this x out. If you wanted to multiply it through, you could. But again, usually they kind of like leave it in that factored form. And I'm going to take this guy. He's going to go down and rewrite it as a radical. Because that's really now 1 minus x squared to the positive half. And that would be my derivative. I'll say this again. I only needed calculus for the first step. The rest is just algebra. Okay. The next one's kind of similar with that setup. Ooh, I see a fraction. What rule am I going to have to use for that? Quotient rule. You betcha. Okay, again, before I even do any derivatives, I see a radical, so I'm thinking that that's the same thing as x squared plus 4 to the 1/3 power. like a power. I can do better. Okay. Product rule. Low. D high times the derivative of my high, which is just 1, minus bracket high D low. All right, gotta use chain rule here to take the derivative of low. That would be 1/3 box, drop 1 from the power, negative 2/3. Inside my box is x squared plus 4. Chain rule times the derivative of that inside, 2x. All over low squared. Low d high minus high d low all over low squared. Okay, let's take this piece by piece again. Now we got some tough algebra. All right, this first piece, I'm just timesing by 1. Nothing I can really do there. I have x squared plus 4 to the 1/3. All right, this. I have x times 1/3 times 2x. So that'd be 2/3 x squared times this. So see how I kind of look for like basically all the common factors that are not in the parentheses and I bring those like in front. All over here when I have a power to a power, what do I do with the powers? Not add.
Subtract.
Not subtract.
Multiply.
Multiply! Nice!
3 times the charge.
Okay, now we're going to do that similar little strategy that we did in the last one, where we're going to factor out x squared plus 4 to the negative 2/3. Okay, I'm going to factor out x squared plus 4 to the negative 2/3. So when I do that, and again, I can kind of do this math over here. When I have this, and I divide out this, when you're dividing, that's when you subtract the powers. I have a similar setup where I'm like, hey, one-third minus negative 2/3, I end up getting the power of 1. So I'm just left with x squared plus 4 there. If you want to write to the power of 1, you can, just for sake of remembering how we got that. Out of this term, I factor that out, so I'm just left with negative 2/3 x squared. Okay, everybody kind of see that? Now what this allows me to do is now move this negative exponent downstairs. Which if I move that downstairs, I have x squared plus 4 to the 2/3, positive 2/3, times x squared plus 4 to the 2/3. And I can multiply those and do what with these powers?
Make them 4/3, add them together.
Add them. Yep, same base. That's exponent property. Same base, add the powers. So I can make that x squared plus 4 to the 4/3. Okay, that's just kind of my denominator. I'll come back to my numerator in a second. Sorry, I didn't give you a ton of room to write on this one. Okay, that's looking good. Now in my numerator, what I end up having is this piece kind of left over. So I have x squared plus 4 minus 2/3 x squared. Now we can't have like fractions within a fraction. We can't have complex fractions. So we could like make common denominators here. We could definitely do that. But another thing we could do is just times the top and bottom by 3 and kind of like get rid of the fractions. Or we can make common denominators. What do you guys want to do? Top and bottom by 3? Okay, that's what I did too. So I move this down now, so I can multiply my top by 3 and my bottom by 3, which that's easy to do. But you could write this too in your work if you want to. Multiply the top and bottom by 3. So there we did that. So that'll give us 3x squared plus 12 minus 2x squared. And then we get a final answer. Now I can add these together. X squared plus 12 in my numerator. Let me just make sure this is right. X squared plus 12 or 3? Yes. There's your derivative. Woofda. Oh no, the bell's gonna ring. Okay. I only have one left in the notes for us to do. We can do that as a warm-up on Monday. And then the rest of the notes are just all basically now all of our differentiable rules, including the chain rule.